Okay, here we are, starting week 2. This week, I'm talking about organizing and presenting data. Let me say first, I'm going to come back to the basic definition here. Statistics is about studies to collect, organize, summarize, analyze, present, and draw conclusions from data in order to solve problems and make decisions. This week, what I want to talk about is the organizing and presenting and those particular aspects of it. Now it's going to be this is a big area, and I'm going to keep it fairly limited here and try and focus some stuff in it. And in fact, what I'm going to try and do mostly is I'm going to try and stick to what's in the book here and say some things about these particular learning objectives, minus the stuff about Excel, because I'm not going to talk too much about Excel, but I will talk about a couple things in here that I think are really important about Excel. Let me start by the first thing in this thing is talking about the difference between raw data, charts, and graphs. Let me start here with an apology a bit. If you remember seeing Pirates of the Caribbean, there's a place early on in the film where the heroine of the thing is captured by the pirates and they're about to kill her, and she goes, "Parlay," and everybody stops. It's just the rules of the code of the pirate code says if I say this, you have to do this. And the response is the beginning of a running joke through all the films is when it says, the code's more like a set of guidelines than a set of rules. Well, I bring that up because that's true in a lot of this area right now. I got into mathematics originally because I thought, oh, isn't it neat that there are clear rules and definitions and guidelines, and you do this, you see this, and it's also clear and precise and always true. And that's not so much true in a lot of statistics. I'm sorry to tell you. And I'll try and point out to you where that's not true here, because there are places here where guidelines it's more like a set of vague guidelines than a set of rules, but be that as it way. This is what raw data looks like. And I'll show you a data set around here. But if it's raw data, it's like you have a certain number of people or cases, and then you have certain measurements against those things. It looks like something like this. There's no summarization. This is just the raw data. A chart for me is something that looks like this. What this is I've summarized the data into categories. I left out height, for instance, here, but I have some categories here. A graph, on the other hand, something looks like this. It has some sort of geometric shape to it, in addition to the numbers. It may or may not have numbers to it. There's a number of things I could criticize about this graph, and it would not be hard. But my intent is to say, I may try and make a distinction between charts and graphs, as well as where the pirate code comes in. I say that, the reason I make the distinction is because if you're using Excel, Excel makes it very hard to graph raw data. There are places where it can. I'm going to try and show you some stuff coming up this week where you can do it you can in fact chart raw data, but mostly Excel requires data to be in charts, some sort of summarized process. Even with that, what'll happen is Excel will sometimes call something a chart when I would call it a graph. And frankly, I do that also. There's two examples that come up here. Pie charts. Pie charts are really graphs by my definition, but everybody calls them pie charts. But for my mind, it's a graph rather than a chart. I'll give an example later about what's called a Pareto chart. Well, Pareto chart is really a graph, but everybody calls it a chart. I just know for you, there's some confusion here. I just want to alert you to the fact that you got to be thinking about, if you're going to graph something, you probably have to turn it into a chart form. That is, you have to do some sort of summarization of the data. If you don't, you'll probably end up with something that looks, you look at it and going, I have no idea what that means, because it doesn't mean much of anything. It's not very useful. I provide a data set here. And what I've done with this data set is something, I've done something to this data set, because the original data set was just here. This first column here, I added to it. And I added this column to it to insert what I called a dummy variable. It isn't that this 21-year-old male here was the first person in the door. It's the first piece of data that I have. This person's no more first than this person or this person. It's happened, pure chance this person ended up first in my data set. However, I end up giving them a number 1, and the second one 2, and so forth. I add this dummy variable, which doesn't mean anything, except that later when I start working with this, what I would do with this is I insert the dummy variable, and then I would save it in my computer. And then what I would do is I would open that file and I would save it under a new name. The reason for that is I'm going to show you a little bit about sorting and doing those sorts of things. You go in and sort data, or you start inserting formulas into an Excel spreadsheet, and sooner or later, you're going to click on this cell right here, and you're going to insert a formula in the middle of it. Just, it happens. And then it's like, oh my God, I don't know what the diagnosis was for that person. Well, then what you can do is you can just close the data set, don't bother saving it, and go back and reopen your original one. That's a discipline that I encourage you to develop if you're going to do much data analysis. Save your original, save it under a new name, and then work with the new named one, because it will save you frustration and angst and craziness later to have your original data set around for when you accidentally screw up the one you're working on. And if you do much data analysis, I guarantee you sooner or later you're going to screw up your data set. And having the original go back to it's worth the 2 minutes it takes you to do this thing in the first place. I just, trust me on this, it'll be well worth your time. So let's talk about sorting data. Here's the data, the original data set here. What I did is I said, well, if I sort it by age at first diagnosis. Well, here it is. Now, the youngest person is first here. Now it's my first, is client number 12. You know, it's like it gives me this stuff. And I look at this and going, okay, what does that tell me? And the answer is, I don't have a clue. Well, what Excel can do for you, it can allow you to sort by more than one variable at a time. And so for instance, what I might do is I sort first by age at first diagnosis and then by sex. So when I have 3 18-year-olds here, I'm sort of the females first and the male second. I got 3 19-year-olds, they're all females. I've got 3 21-year-olds, I got the females first. They can be what I want. And I don't know what you want here exactly, but maybe or maybe not. And I can tell you truthfully, I end up going through and sorting 2 or 3 ways before I finally say, oh, that's helpful. For instance, I think here, sorting first by sex and then age at first diagnosis is more useful, because then I have all the females together and I have all the males together. In Excel, what I could do is I could go in here and insert a column in here and then figure out the average row that I inserted here. I said insert a column, I meant insert a row here. I go through them, I can say, what's the average age of everybody, all the females? And I have that pop up here. And down here, I can say, what's the average age of all the males? And be able to compare males versus females in terms of age, or in terms of age at first diagnosis, or height or weight, who knows? But it's a way of, sometimes, particularly gender is often a very useful way to sort things. And it's a very useful organizational tool to learn to work with. The other way to organize is organizing stuff into categories. This is how you turn raw data into charts. Your categories have to be mutually exclusive because you don't want the same data point, two different things. They have to be continuous, as you don't want any gaps. For instance, I say here, you don't want your categories to be age 20 to 29 and the ages 32 to 39, because what happens if you're a 31-year-old? You want to be exhaustive. You want your categories to include all the points in your data system, and you want to be of equal width. That becomes really important. Now, one of the other things that's going to come up here is a thing called class limits and class boundaries. A class limit is the largest and smallest values that are counted in a group. These are actual data points. There may or may not be a data point there, but it could be one. A class boundary you will never see as a data point, as a real data point. The class boundaries are halfway between the different categories. That becomes important because I'm going to show you how to get at a data analysis software within Excel. And it will do some of the sorting. It will create some of these categories for you, but you got to tell it how many categories you want. But you got to be clear where you want the boundaries to be, and you may have to tell it what you want the boundaries to be. Those are different concepts, by the way. They're just important to be conscious of it. These things tend to lead to what we call frequency distributions, and there's 4 or 5 ways of having frequency distributions. Let me go back here. I'm going to drop out of here and jump back. This is a raw data. Over here, this is a frequency distribution. The frequency is the number of people who fall in that category. 2 people fall in the category of 50. Go back over here and say, oh, well, there's one of 41 and there's one of 45. I was sort of adding a 6th person here at one point to play with this, but this is a frequency. What's the frequency that's of cases in each of the categories? A graph like this, a histogram, is a visual representation of a frequency distribution. This is what the frequency distribution looks like. You could do it either way, and both would be correct. The thing is, this kind of way tends to be easier for people to make some sense out of. Now, I've only got 3 categories like I have over here. This is not a big deal. You're going to go, Steve, most of us can follow that. What if I have 10 categories? Then you're processing, actually the way this is set up, you're maybe processing as many 20 numbers, the number of people and the age. It's like there's a lot of data you're playing with in that. And people have some trouble with that at times. This sort of thing is easier to make sense of. It's easier to visually process. And it sort of absolutely it helps you organize what you're looking at. And that's worthwhile doing. So a frequency distribution, it's just the number of categories with the frequency that something occurs in them. Then you have a thing called a relatively frequency distribution. It's a proportion. The proportion of cases that fall into this case. So here is like, here's a frequency distribution here. Here's the age ranges for things. There are 14 cases overall, 2 in this category, 5 in this, 5 in this, 1 and 1. A cumulative frequency distribution, I'm sorry, a proportional one, adds up the totals and divides the frequency by the total. You divide 2 by 14, you get 0.14. So about 14% of the cases fall in this category. Almost 36% of the cases fall in this category. About 36 fall in here, 7% here, 7% here. It's a proportional frequency distribution. Why is that important? Well, let me stop that one and go back here and say, suppose I want to give you a pie chart or a pie graph, if you more accurately. This is actual data from students one year. I asked people, how do you feel about taking this course, and gave these categories. And this is what students in my class said. About 21% of them felt okay about it. And about 26% were actually excited about it. And about 16% were terrified about it. The thing about this is these numbers add up to 100%. To get, even if you had numbers in here rather than percents, with a pie graph, you're talking about 100% of the course. And this, you could do this in a histogram format also, but this tends to show the proportions much better than a pie graph does. And it's a place where I use pie charts, pie graphs a lot, is where I'm talking about proportions of something. Where I'm talking about, well, 100% of them are here, but I want you to pay attention to what proportion of people walk into this terrified or anxious, for instance, those two things. That I want to see, this is the part that show up there. That's why I use it. That's the that's the proportional frequency distribution. Then you have a thing called a cumulative frequency distribution. The numbers here come from these over here. This number here is this number, the same as the first thing. The second number is equal to this one plus this one. 2 plus 5 gives you the 7. 7 plus the 5 gives you 12. 12 plus 1 gives you 13. 13 plus 1 gives you 14. It's a cumulative frequency. It essentially tells you how many cases are up to that point. And that's really useful to think about some places, particularly when we get into looking at probabilities later. This will become much more important. Just as you have a cumulative frequency distribution, you can have a cumulative proportion distribution. 0.143 is the same here. 0.50 is 143 plus 357. So basically, in this case, what it says is half my cases are 29 or less. Quick way of getting there with a cumulative proportion. This one, by the way, these F prop, CF, and C prop, those are symbols that typically come up for talking about these kinds of distributions. I'm going to jump way ahead here to an example near the end of this thing to give you an example of a cumulative proportional distribution. This is a cumulative proportional distribution about how the mortality of ash trees once we get an infestation of the emerald ash borer. I happen to know a bit about this for a number of years. I've been a first detector for the emerald ash borer in the state of Vermont. If you don't know about the emerald ash borer, it's a little tiny, about the size of a quarter, luminescent green beetle. That in some ways is it's very pretty, except that it eats ash trees and reproduces all the time, it seems like. And once ash trees get infested, they die. We have almost no defense against the emerald ash borer at all. As this chart from Davy comes up, it says, what tends to happen when you get an emerald ash borer in an area? Well, what proportion of the trees die? Well, the first 6-7 years, and this, less than 10% of the trees die. So you can have an emerald ash borer infestation, and you might not even notice it for 5 years. But if you get to year 8, what's going to happen in the next 4 years is you're going to have about 90% of your trees die, 85% of your trees die in that period of time. If you catch the emerald ash borer back here, you can slow it down. If you find the emerald ash borer at this point, harvest your ash trees right away because they're going to die. What this thing here is a cumulative frequency, cumulative proportional frequency distribution. Up at the top here is 100%, all the cases. Basically what this thing says is you get to year 16 and 100% of the ash trees in the area are dead. There turns out that it may only be 99.99% at this point, because maybe 1/100% don't die from it, but it's a very small proportion. Given that we have millions of ash trees in the state of Vermont, this is kind of a big deal for us. This kind of distribution, by the way, is also known as an ogive. I have no idea where that name comes from. It's a funny name. I mentioned it because someplace you may say, well, I have an ogive for that. And you're going, what is an ogive? Should we take an acid for that or something? You know, ogives are a particular name for this kind of distribution. And its characteristic is an S shape in this process. And it's sort of a lazy S here. That's a cumulative proportional frequency distribution. What was I thinking? I also want to mention a bit about outliers. Sometimes you get a distribution that looks like this, you know, that here's the major distribution here. And there's somebody out here, one case out here, which is really significantly different than everybody else. And the question is, well, what do I do with that? Well, there's two things that you can do with that. One is you can say, that shouldn't be in here. You can pull the data out. And people do that. Sometimes you get distributions and say this person should not, this outlier should not be in this distribution. It's a a very unusual case, and adding it in distorts everything else is here. So you can exclude it. Some people do that. The other way of coming at it is to say, let's study this one here a little more carefully and figure out, why is this person so different? If you will. One of the things, for instance, about going back to the example, it's talking about emerald ash borer. If I go to an area around Detroit, Michigan, which is where the ash borer first arrived in the United States, and I drive around Detroit, Michigan, which I tell you the truth is, I'm not going to see many ash trees. In fact, I'm hardly going to see any ash trees, because 100%, supposedly 100% of them are dead. But if I find an ash tree in Detroit, that ash tree is probably worth studying, because for some reason, it's an outlier. It survived when the other ones didn't. So I want to know, what's going on with that ash tree? Why did this ash tree survive when everybody else died? And that's an important question at some point to think about. We need to be thinking about those things. I want to talk a little bit about, I'll give you an example here. I'm not going to go through that one. You can read that stuff. I'm not talking about ogives. There's some stuff here about boundary limits and boundaries and limits for, you can read that stuff over. I also want to talk a bit about another type of graph that's called a chart. And that is, I want to talk about the Pareto principle and the Pareto chart. The Pareto chart is essentially a frequency histogram. It's really a graph. I recently, not too long ago, I read an article about New York City prisons that said they have 37,000 inmates in 5 years. However, 400 of these people out of the 37,000 were incarcerated 18 times or more in 5 years. What it is a relatively small number, and sometimes it's known as the 80-20 rule. A relatively small number of cases tend to account for a large percentage of the intakes in the New York City prisons. What they started saying is they went, well, let's look at these few and see what's special about them, because they're the ones who are taking up most of our intake time. I'll give you an example here. Suppose you're at Vermont Widget, and I ask you, what kind of problems does Vermont Widget happen? You go around and you notice things and you record stuff, and you come back and say, so there's 5 different kinds of problems you tend to have around here: A, B, C, D, and E. And you do a little chart, do a graph and say, here's what those things are. Now, a Pareto graph is real simple. That what it does is it takes the same thing, but it just changes it so the biggest one comes first. It looks like this. Now, why do you do it? Because visually, it communicates the issue much more where you should be focusing your energy. Remember at the beginning of the chapter, I said, statistics is about presenting data. You can present it this way, and this one says, this visually, what it says to you is, you ought to deal with this one first. That's what it says. And you ought to deal with this, one of these two second, and you deal with these things last. Visually, you say that without ever saying a word. It's a presentation of the process that really makes some sense of it. And that's worth thinking about to some extent. Sometimes you want to change how you present stuff because the presentation of it helps make better sense of it. I also want to talk about one other kind of quick thing here, and that is about skewed data. And this is particularly out because right now we have the COVID cases in Vermont. This is skewed data, is skewed right. There's a point to the left where there are no cases. And then there's a big upsurge in this, and then there's this sort of dribbling off to the right. This would be considered skewed right. That it's almost like there's a screw or a skew going out to the right here. You could also have skewed left data. That becomes, it's useful things to think about as opposed to, let's see if I can, okay, gonna get some excitement here. I'm gonna draw for you. Typically with continuous data, what you have, and you've got this axis, typically with continuous data, what most often happens is you get something that looks something like without the bumps. And that's a little skewed. Not trying not to skew it here, but look at my drawing skills. It looks, a normal data distribution tends to be fairly symmetric around the middle. If it goes out much further to one side or the other side, it's considered to be skewed data. And that suggests that there's something unusual about this data that needs to be looked at. There was I have a study that I read not terribly long ago, which I found somewhat interesting, not because the content interested me, but because it was an unusual research question. The data was interesting. The question in the data was, how many sexual partners do you think you'll have in your lifetime? Now, this is a question that never quite occurred to me, frankly, but they asked us a number of people, and what they found that what the data distribution looked like was this. Most people say maybe 1 to 3 or 4 or 5, maybe it may be 10 or 12. But there are people who were saying the answer to this question was 250, 350. The data was deeply skewed right. This is not what I'll come up with later points. We'll talk about a normal distribution. This is not a normal distribution. This is a skewed distribution. And it says something about, well, this is an unusual way of looking at it. There's something about this data that's worth thinking about. It tells you something about the underlying question. And I'm not always sure I understand what it tells me. But I like to look at the distributions because they sometimes tell us information that's worth thinking about in the process. So that's an overview of the week. There's a lot of places here where there are some rules about how to do things, and then there are lots of places where it's like some of the rules, for instance, about categories. No empty spots in the middle of categories. All your categories are the same size. Things like that are rules that you really want to do. I include a video or a paper this week about how to lie with statistics. And it shows you some things that are The rules are no, you don't do that because that's deceptive. Um, your data looks good, your distribution looks good, but it's not telling an honest, it's not saying, somewhat saying it's dishonest ultimately. And I encourage you to look at that because I'll give some real examples of that and some things that I've actually seen people do in the process, and something I pulled off of a U.S. Senator's website that he showed people about something that's like, and I also include a report that I pulled off WCAX from a couple of years ago about how people feel about DCF in Vermont. And I think the graphs they provide are deceptive. I think they say something that I don't think is true. And I ask you to look at that and try to make some sense out of that for yourself. And what do you think about it, where it is? And that's the stuff I want you thinking about this week and thinking about how do you organize, pull it together. We're not even doing any analysis yet. We're just sort of organize it to try to say, what does it look like and what do I got here exactly? And that's what this week is all about. Look forward to talking to you online.